Welcome back. Thermodynamics, lecture 3.2, where I'm going to talk about the international temperature scale. And we're going to talk a little bit more about equations of state. All right. So last time we talked about thermometers and we talked about temperature scales and how we can imagine this entire spectrum of temperatures. We talked about from picokelvin nuclear spins all the way up to 10 to the 7 Kelvin, the temperature of the sun. So the question is, so now we know how to define temperature. We know that we can compare temperature scales. And we need fixed points for this, right? And we need thermometers that work accurately in these ranges, right? So the question now is, if I'm an international body, right, and I need to define the temperature, right? So this is the System International. So if the SI unit system wants to define the temperature scale, how do we do that? Can I use a single thermometer for the whole range? Last time we talked about the ideal gas thermometer, and it's very good, but you can already see that even if we were to use gaseous helium as our ideal gas, we would never get it all the way down to 0 Kelvin. It would liquefy at 4.2 Kelvin, right? So we couldn't have an ideal gas if we have a liquid. And probably a little bit above that, it's even starting to be non-ideal, right? So when you start to get enough attractions that it's thinking about. So to define an international temperature scale, we actually need a number of thermometers, right? And so what we actually have is called the ITS 90. So I'm going to actually post the ITS 90 so you can take a look at it in all of its glory. This is the International Temperature Scale, which was defined in 1990 or accepted in 1990. And it is, let me write the definition, an approximation of the thermodynamic can't read my handwriting. What's the next word? The thermodynamic, I don't know, scale, I guess. Scale that facilitates the comparison of temperature measurements. I like that. So it's an approximation of the thermodynamic scale, but it actually facilitates comparison of temperature measurements. So it means it can be reproducible from lab to lab, from situation to situation. It can be controlled, but also has some overlapping ranges, so one thermometer can measure and compare with another in some temperature range. Okay? It consists of 14 fixed points. Between 0.65 Kelvin and 1,358 Kelvin. So it uses helium vapor pressure, so basically this ideal gas we were talking about. So it actually uses the vapor pressure above liquid in some temperature ranges, which is something else we'll talk about later. It uses helium as an ideal gas. It uses the resistance of platinum, so platinum resistance thermometer. It uses radiation, and it also often uses interpolation, right? So this is a key factor. Wow, it's quite amazing to me that we showed all those various temperatures that we could have in the temperature scales, and that it stops at 0.065 Kelvin. So I am particularly intrigued by this and interested in this. And so there is something we call the PLTS 2000, the provisional low temperature scale. It adds the properties of the rare isotope, helium-3, to the temperature scale, and it allows it to extend the definition down to, I believe, 0.9 Kelvin. So 900 millikelvin. Sorry, 900, nope. So 0.0009 Kelvin. So 900 microkelvin. So less than a Kelvin, less than a millikelvin. So this is controversial, though. Actually, not everybody in my community uses the PLS 2000, including me. There's some things about it that I definitely do not like. And I'm actually really interested in my lab in coming up with some new thermometers that can work to help define temperature scale below 0.65 Kelvin. I think that would be really cool to be a part of. Okay. So let's actually stop there. Let's call that the international temperature scale. And actually, we'll do the equation of state in the next lecture.